SI units, 17 centimeters is 0.17 meters above the ground. So your mechanical energy at the highest point is going to be 0.750 joules. So now let's find what is your mechanical energy at the lowest point. So again, we're using the floor as the reference height. We determined at the lowest point we had kinetic energy and potential energy. So that's equal to EP plus EK. Our potential energy is mgh plus our kinetic energy, 1/2 mv squared. Alright, what we can do here now is we can plug in what we know. We have a mass of 0.450 kilograms times 9.81 meters per second squared times a height of 11 centimeters from the floor, or 0.11 meters, plus 1/2 times the mass again, 450 kilograms, times the velocity squared. We don't have velocity. Even though we don't have velocity, we can still solve this problem. What we were going through and doing, or what I was trying to go through and doing, was showing you the long way of solving this problem. But since we already know that at one point, at your highest point, you have a mechanical energy of 0.750 joules, we know at any point you're going to have the same mechanical energy. Your potential energy and your kinetic energy will change, but your mechanical energy is conserved. It's always the same, 0.750 joules. So as frustrating as it may be, all of this, not important. We know if you can solve for your mechanical energy at any point, it's going to be the same at any point. So in here we had our problem. We wanted to figure out what is the speed at the lowest point. We didn't know that. Alright, my apologies if this seems a little choppy at this point of the video. The audio is getting a little goofy again, so I'm redoing it in hopes that the audio stays a little better. Alright, so we want to determine what is the speed of the pendulum when it is at its lowest point. That's what we were doing over here. We were figuring out at its lowest point what its mechanical energy was, but we didn't know the speed. Now we want to solve for what is the speed. Alright, we know that the mechanical energy when it's at its highest point is going to be equal to its mechanical energy at its lowest point. We have our conservation of energy here, our conservation of mechanical energy. What it's like at one point is equal to what it's like at a second point. So if we're using our highest point there, we have the potential energy at its highest point is equal to the mechanical energy at its lowest point, or its potential energy at its lowest point, plus its kinetic energy, 1/2 mv squared at its lowest point, or just the energy kinetic. I'm getting ahead of myself. So now if we're plugging in our formulas for this, we have mgh at its highest point is equal to mgh at its lowest point plus 1/2 mv squared. We're going to want to rearrange this and solve for v. Since we have mass in all of the terms, we can go ahead and cancel out mass. Now we're left with all of this over here. We're going to subtract from both sides, and that's going to leave us with gh at its highest minus gh at its lowest. We have 1/2, so we're going to multiply by 2, and we are going to take the square root to cancel out the squared. So velocity is equal to 2, or is equal to the square root of 2 times g at its highest height minus g and the lowest height. Alright, when we're plugging in, we have 2 times 9.81 meters per second squared times the highest point of our height is 0.17 meters minus our lowest point, or sorry, our gravity, 9.81 meters per second squared, minus our lowest point, 0.11 meters. And we're going to take the square root of all of that. When you take the square root of all of that, you're going to get an answer of 1.08 meters per second. Alright, so this question was chopped up a little bit from video to video. If it was a little confusing, if it didn't make sense, please let me know. I'm happy to help you with it. Alright, in this next example, you have an 1100 kilogram roller coaster traveling on a frictionless track as shown to the right. A big word you want to notice here is this frictionless track. That means there's no external forces acting on it. In other words, it's an isolated system. Because it's an isolated system, we are going to have the conservation of mechanical energy. The mechanical energy at one point is going to be equal to the mechanical energy at any other point, or a second point. So, if the roller coaster starts from rest from a point A, we want to determine the type of energy it had at each point. So at point A here, it's at rest. It's not moving. There's no speed, so it's all potential energy. Alright? As it comes down, it gains speed and it hits this point here, point B. Or what should be point B. Point B, there is a height still of 2 meters, so you have potential energy plus kinetic energy. That's if you're using the ground as a reference. If you're using the lowest point as a reference, which I don't recommend in this example, it would be all kinetic energy. Alright, so for the purposes of it, I'm going to keep the ground as the reference point. So it keeps going and it comes back up and it's at C. Because it comes back up, it's probably not going to be moving as fast, but it's still going to be moving. It's still going to have a kinetic energy. And because there's a height, you're going to have potential energy. Alright. So number 2 wants us to find out what is the mechanical energy at point A, point B, and point C. At point A, the mechanical energy is equal to all potential energy. It's only potential energy. Remember, there's no speed, there's no movement. So that's going to be equal to mgh, which we can just plug in and solve. We have 1100 kilograms times 9.81 meters per second squared times 12 meters is our height. When you solve, the mechanical energy at point 1 is 1.29, or point A is 1.29 times 10 to the 5 joules. At point B, because we have an isolated system, we know that the mechanical energy at point A is equal to the mechanical energy at point B. Our mechanical energy at point A was 1.29 times 10 to the 5 joules. And because again this is an isolated system, I'm guessing you're going to find out pretty easily what is the mechanical energy at point C. At point C, the mechanical energy of A is equal to the mechanical energy at C, which is also equal to the mechanical energy at B, which is equal to the mechanical energy at any point in the system, which is always going to be 1.29 times 10 to the 5 joules. Alright, we want to determine though now, what is the speed at point B and point C? So at point B, again, we know the mechanical energy at point A is equal to the mechanical energy at point B. At point A, it was all potential energy. Alright, so it was EP is equal, at point A, is equal to, at point B, we have potential and kinetic energy. Is equal to the potential energy at point B plus the kinetic energy at point B. We can now plug in our formulas and see if we can rearrange and solve for velocity. So we have mgh of A is equal to mgh of B plus 1/2 mv squared. We have mass in all three terms, so we can cancel out mass. Alright, and we want to solve or rearrange and solve for velocity. Velocity is going to rearrange to the square root of 2 times GHA minus GHB. Alright, so its velocity at point A is going to be the square root of 2 times 9.81 meters per second squared times 12.0 meters is our height at point A minus 9.81 meters per second squared times our height at point B, 2 meters, times 2.0 meters. When you plug that all in and take the square root, your velocity at point A is equal to 14.0 meters per second. Alright, so let's now look at solving for the velocity at point C. So this here was the velocity. Oh geez, I messed up the whole time. The velocity at point B. So we're going to take now and look for what is the velocity at point C. Alright, I'm going to be a little sneaky and change up what we do on this problem to make it a little easier. So I'm going to change now to make our reference height to being right here at point C. That means at point C, this is now going to be 0 meters, and point A relative to point C is 12 minus 4, or 8 meters. So the height for A is now going to be 8 meters instead. You can continue and you can do point C the same way we did before, but I'm going to show you a little trick if you're comfortable with it for doing it a little quicker and a little easier. So the reason I do this is because we still have the mechanical energy at point A is equal to the mechanical energy at point C, but now since there is no height, we are going to have all kinetic energy. We don't have potential energy there. So at point A, remember it's not moving, so it's all potential energy is equal to point C, which now has no height, it's all kinetic energy.